Absolutely. Oh yeah, it'd be super annoying. Yeah, I want to make sure that y'all consider this scenario very much to the fullest, because as soon as you walk out of the classroom today, whatever you choose is going to be applied to you by a magical thing at the door. So choose wisely. Before we get started, Evan asked me to make an announcement. I think it's through the engineering department or through the computer science department. Mathematics department. Okay, so through the math department, they're offering a class this fall on Fourier analysis. So if you have any interest on some of the stuff we talked about in terms of determining specific frequencies and the like, there's a mathematics class on Fourier analysis, but it currently doesn't have enough people in it to make necessarily. So how many more do you need? Like 4? Okay. If 4 more people will sign up for the class will make. 15 is the number I've kind of been told. So if you get to 15 folks signed up for a class, then you're more likely to have it offered. So sign up for Fourier analysis if you have questions. Evan, raise your hand. Talk to Evan after class, and he will give you all the details that you need. Okay, so we talked about last time alternating currents with resistors and inductors and capacitors all individually inside of a single circuit. And so the next logical step that we get to talk about at this point is what happens if instead we start adding in multiple elements into the same circuit. Now, I'll go ahead and tell you and forewarn you that you get into some complicated differential equations if you start adding multiple branches and multiple elements along each branch. So we're just going to stick to the most basic circuits today. And we're going to look at LC circuits. LC circuits, but without any generator in it whatsoever. So this is going to be an undriven LC circuit. And what I mean by that is, leaving the Quickly code up there, I know you can't see the image behind there, but I'll take the Quickly code down in a second. If you look on your devices, if you scanned in, all that this circuit has is a resistor, an inductor and a capacitor in it. And the capacitor is going to be initially charged to some value Q naught. And we're going to charge it up by some mechanism not shown in this figure. And then we'll disconnect the thing that charges the capacitor and we'll close the circuit. So that way current is now allowed to flow along the conductors in the circuit. And taking Kirchhoff's loop rule, what you get around this circuit, meant to minimize that. What you get going around this circuit is you get a voltage drop going across the circuit here, where the voltage drop is going to be Q over C. That was what we discussed in terms of the relation. Don't forget that C is equal to Q over V, so we can calculate the voltage drop based off of the definition of capacitance. And then from the definition of inductance in an inductor, we can calculate the voltage drop across the inductor is going to be equal to L times the change in current with respect to time. But what we have to consider is that the current inside of the inductor, or anywhere in the circuit for that matter, is going to be the change in charge with respect to time, meaning that we arrive at this differential equation, d squared q over dt squared is equal to minus 1 over LCQ. And so, if you don't know differential equations, this is a very intimidating looking equation. You have the second derivative here is equal to the function itself multiplied by a constant. And that constant is minus 1 over LC. And so, assuming that most of you have not taken DiffyQ yet, how in the world do we end up solving this complicated mess here on the screen? What? You interpolate. Okay. Yeah, if you know how to use Python or MATLAB, you stick it into an ODE solver and you let MATLAB or Python or C++ or some other system solve it for you. But let's assume that most people don't know how to do that either, right? The second derivative is proportional to the function itself. Another way to think about it is, if you take the second derivative of the function, you get the function back with a constant. Okay. Without any knowledge of differential equations, what functions do we know that you can take the second derivative of that function and get the function back? What's that? Sines and cosines, exponential functions, right? Either one of those are going to fit, an exponential function or a sine or cosine function. As far as we're concerned, because that little negative pops up, and you can convince yourself that this is true, and we'll do that here in just a second, what we're going to be looking at is the solution is either going to be a sine or a cosine function, not the exponential function. Because if it's an exponential function, if the argument is positive, well, when you take the second derivative, you'd get a positive out front here. And if the argument is negative, then you get a negative when you take the first derivative. You get a negative again when you take the second derivative. The two negatives cancel out and you still get a positive. And so that leaves us with sine or cosine as our solution to this differential equation. Are y'all tracking with me here? Another way to say it is, let's assume that the function is a cosine function. Take the first derivative. The first derivative of cosine is minus sine. The derivative of minus sine is minus cosine. And so, yeah, if our function is cosine, taking the second derivative, we have the negative sign that we end up needing. So the form that we're going to work with here is that the function itself for the amount of charge on the capacitor at any given time is going to be A, where A is just the amplitude, and we'll figure out what that is here in a second. A is the amplitude times cosine omega t. We don't know what omega is yet. It's just the angular frequency of oscillation of how the system is going to oscillate charge on the capacitor. So you can imagine if it starts with plus Q naught on the top plate, sometime later the system is going to completely reverse and you are going to have plus Q on the bottom plate or negative Q on the top plate, however you want to think about it. But it's just going to keep oscillating back and forth with the positive charge being on the top plate to bottom plate and back and forth. So cosine omega t minus delta. Delta is just a, how can I say this? When you do differential equations, if you take that class or have already taken the class, for the order of differential equation that you have, meaning that the order of derivative that you have, this would be a second order differential equation, you will find that you have to have two undetermined constants of integration for every derivative, one undetermined constant for every derivative that you have. So we've got two derivatives, we have two undetermined constants. For us, that's going to be the amplitude and it's going to be the phase. But if the capacitor starts fully charged, cosine is maximized when delta is zero, when there is zero phase shift, right? I mean, if I open up Desmos here, just like we've done several times before, open up the graphing calculator, and I say that, let's see here, A times the cosine of omega x minus delta. Will it let me do delta? No. Omega x minus d. Right? Then setting omega is going to adjust how close together the wave is. As omega increases, you get more oscillations per second, right? And if, let's start with d is 0. The amplitude is just going to be how much charge you can have when the charge is maximized. And that's just going to be determined by, we'll see here in a second, how much charge is on the capacitor to begin with. I'll do the math for you here. But you can see that if we add more charge, it does not change the period of oscillation. It just changes how much current there is, how much charge there is to work with to begin with. And then the last thing is delta. And you can see that as I move delta, as I change the phase shift here, then let's say if I go to a phase shift of pi, let me go to omega equals 1, there we go. If I go to a phase shift of 0, you can see I've got my initial wave where I start with a fully charged capacitor. But if I change delta to any other value, then I'm starting with a less than fully charged capacitor that somehow goes up to fully charged, which doesn't make sense if we said that it starts fully charged to begin with. So what I'm trying to say is that for us, in the sense that we were told our initial conditions is that the capacitor starts fully charged, delta has to be 0 here. Okay? So let's go in and take a look at this one more time and prove to ourselves that this is a valid solution to the differential equation. The differential equation, if we go back one term, was d squared q over dt squared equals minus 1 over LC cubed. 1 over LC cubed. So let's write that down. Oh, come on. Okay, so what we get is the differential equation was d squared q over dt squared equals minus 1 over LC times q. And we said that q is going to be equal to a times the cosine of omega t minus delta. And so dq dt is equal to minus omega a sine of omega t minus delta using the chain rule there. And then d squared q dt squared is going to be equal to minus omega squared a cosine omega t using the chain rule again. So let's plug that back into our equation here. Plugging that in, I get minus omega squared a cosine omega t minus delta equals minus 1 over LC times q, which is just a cosine omega t minus delta. Well, I can divide by -1 on both sides. That gets rid of my negative sign. I can divide by a cosine omega t on both sides. And that means that omega squared is equal to 1 over LC. Or omega is equal to the square root of 1 over LC. Or you'll see it written in your textbook as 1 over the square root of LC, making all mathematics majors happy everywhere, that we leave a radical in the bottom, in the denominator. We just do it as physicists to get on the mathematicians' nerves. Yeah. So, I don't know if you picked up on it, but I said we have two undetermined constants of integration. And if you were counting, there were 1, to three constants in the equation. It turns out that omega is not undefined. Omega is determined by the differential equation itself. So A and delta are undefined constants of integration, just like I said. So how do we calculate what those undetermined constants are? Well, the way that you determine undetermined constants is now Q at time 0 is equal to Q naught, right? That's what we were told here at the beginning of the problem. And that's equal to A cosine omega, we already know what omega is, times t minus delta. But if we start with maximum charge, right? If we start with maximum charge on the inductor, on the capacitor, then that means that the first derivative of Q at time t equals 0 has to be 0. Right? If it's a maximum, that means that the first derivative has to be 0. That's our definition of maximum all the way back from Calculus 1. Which means that minus omega A sine omega t minus delta is equal to 0. So we now have these two equations with two unknowns to help us determine what A and delta are. Are you tracking with me? Any questions so far? It doesn't have to be. In this case, we determined that it was. One way that we could break this is if instead of hooking something up to the capacitor to start the capacitor with some initial charge with the switch broken, you could instead have something tuning up the inductor. You hook something up to the inductor so that way you get some current flowing through the inductor, and then you switch to the isolated LC circuit. That would break this assumption, and we would have two different conditions here that we would have to satisfy that would give us different values of A and delta. But for this one, by the setup, the setup told us that we started with a fully charged, a maximally charged capacitor. Other questions? Don't know what questions to ask? Way deeper than you ever wanted to go? I think that's what Elsa's song is about, right? Into the unknown. She was a physicist at heart and just wanted to know more about the world around her. Yes? Yes. So one, well, not necessarily. You could have any solution here to these. You could find that A could be 2Q naught, and delta could be pi over 4. Okay, so when it's at its maximum, we're going back to, I think you're getting ahead of me here. What I just showed you on the graph is if we want it to be a maximum, then the first thing that we have to consider is this statement right here, the bottom statement. That the only way that this statement is satisfied, the bottom statement, is if delta is 0. Right? That's the mathematical way to show you that shift that I was doing with delta on the Desmos slide. Which is the same thing what you're saying, but the way that you show that mathematically is with this statement right here. That the first derivative is 0 because we need the argument of the sign to be 0. Right? If I show the same thing here, on our Desmos slide. Now I want minus WA sine omega t minus delta. Whoops, that's supposed to be x, you're right. Yeah, so you can see the only way that I get the slope to be 0, meaning that I'm at a maximum for my cosine, is if delta is 0. So same thing as what you're saying, same thing as what I showed before. I'm just doing it with knowing that the first derivative has to be 0 if it's maximized. I guess another way that I'm trying to say it is, you're correct. We want the cosine to be maximized. And the way that we would calculate that mathematically is with this second statement right here. And so that means that this term right here is also 0, which means that cosine of t equals 0, if we let t equals 0 here, then cosine is equal to 1, and that means that A is equal to Q naught. Or that the most correct form for this setup for Q is equal to Q naught times cosine omega t. This is, for this setup, the final solution for what the charge on the capacitor is as a function of time. Okay. Let's go back to our slides here. So, sorry, yes? What? Quickly? I will quickly throw it back up there. No problem. Do what? Couldn't help myself. I had to, being one of the professors who's piloting Quickly, I had to fill out a survey about how it's going using Quickly. And so I tried to use as many Quickly puns as I could in my survey results. Students are able to quickly scan the QR code. I mean, I can't remember all of them off the top of my head, but I was very proud of myself. I saw a quote, I read a quote in a book last night. I couldn't sleep last night, so I was up at like 2 in the morning reading. And someone in this book said, the only reasons that puns are not funny is because you didn't think of it first. I was like, yes, that is so true. Puns are most funny to the person that thought of it. I don't know. Gnaw on that for a little while you're running scared from differential equations in your physics class. Okay. So I showed you that we could take the derivative, right, to figure out what all of this is, but it just so happens that if we take the derivative, we said that that was dq dt, and that's the current. So knowing what the charge is on the capacitor, we know what the current is through the system as a function of time. The current itself is oscillating. It's going back and forth, back and forth. And since we're assuming that these are ideal capacitors and ideal inductors, it will do this indefinitely. For the rest of time, it will do this. Now, we know that unless these are made with superconductors, right, that have zero resistance, then there's going to be some minimal resistance just due to the fact that you're using a copper wire in the system, and it will dissipate energy over time, and this will eventually decay. But right now, the current, in this ideal sense, will oscillate forever, back and forth. And what's more interesting to me is that the energy inside of the capacitor, we said that before, when we first introduced ourselves to capacitor, we called this the electrical energy stored inside the capacitor, is equal to 1/2 Q squared over C. And if you substitute in our solution for Q that we showed on the notebook slide, That's 1/2 Q naught squared over C times cosine squared omega t. And the energy stored in the inductor, we called that the stored magnetic energy. And the stored magnetic energy is equal to 1/2 Li squared. We determined back at the tail end of last unit. And the current, the max current at least, you could show is going to be equal to omega Q naught. So we make that substitution, and we get 1/2 L times omega Q naught squared sine squared omega t. Which means that the total energy in the system at any given time is equal to 1/2 Q naught squared over C. Okay, where did my sine and cosine terms go? If you imagine that the total current is going to be the the total energy stored in the system is equal to the magnetic energy plus the electric energy, right? The energy has to be somewhere, so it's going to be the sum of the electric and magnetic energy. Where did the sine and cosine terms go? Yes, sine squared plus cosine squared equals 1. And so, if you look at omega, omega was equal to 1 over square root c. Let's write these down really quickly. I'm gonna pull my notebook over to the side here really quickly so I can actually write these down. And then I can't. This other screen is not writable. Never mind. I can do this another way. That's fine. We've got here that U sub E, we said, was equal to 1/2 Q squared, Q squared over C, and that was Q naught squared times cosine squared omega t. And U sub M was equal to 1/2 times L times omega squared times Q naught squared times sine squared omega t. And if we want the total energy, then that's equal to, why write it down twice? Let's just do it this way. Lasso tool, Control C, cursor there, Control V. Boom. Plus 1/2 times L, omega squared, that's going to be 1 over LC squared times Q naught squared, sine squared omega t. Or let's propagate that into the system. So that's L squared C squared in the denominator. Am I missing something here? I don't think so. Let's see. That cancels that. But why do I have an extra factor of C? What happens to my extra factor of C? Yo. Oh, yes. Thank you. Yeah, omega is equal to 1 over the square root of LC. So that means omega squared is equal to 1 over LC. Thank you. Good call. Yay. They ate Sir Robin's minstrels, and there was much rejoicing. So that's 1/2 times Q naught squared over C times cosine squared omega t plus sine squared omega t, and yes, that's just one. You learned that trigonometric identity way back however many years ago or semesters ago, and you thought you'd never find it useful. Well, physics is here to prove you wrong today. How exciting, right? You're shaking your head, but I know you asked your peers and your teacher, when am I ever going to need to know this? Today is that day. Right? Like Aragorn at the end of the Return of the King, right? Except today is not that day, so I guess I got it backwards. But that's one of the greatest speeches in all of fantasy fiction, right? I mean, that's just, and Viggo Mortensen does a great job delivering that speech. It's kind of like, man, my brain's all over the place today. William Wallace in Braveheart, right? Yeah, same kind of thing. Without the mooning of the enemy, but I digress. Man, I'm telling you guys, my mind is a strange place. And if you're utterly bored by all my movie references, I apologize. Yeah. What you know, a physicist either was crazy to become a physicist in the first place or went crazy somewhere along the way. But be that as it may, they're crazy. If a resistor is added to the system, then the resistor will dissipate the stored energy over time, and the result is what is called a decaying oscillation, meaning that you start with some Q naught on your first oscillation, but by the time you get to your next oscillation, maybe you have Q naught over, you've lost some initial charge, maybe a tenth of your initial charge, so you're at now 9/10, and the next time you're at 8/10, and then 7/10, and eventually you'll decay off to 0. It turns out that it's an exponential decay if you solve the differential equation. That requires more big boy and girl mathematics than just throwing a solution at it and hoping that it sticks. So we're not going to do that here, but trust me on this. Take me for advanced mechanics if you want to see it, and if I'm actually teaching advanced mechanics. But the result is something that looks like this for the charge and the current respectively. That you can see it is a sine wave underneath here. There is a sine wave that sits underneath here. But what ends up happening is you can actually map this out, that the decay is exponential. And the exponential decay forms an envelope around the sinusoid. And so you get that there is a decaying exponential function multiplied onto the sinusoid. Sinusoid, new word for the day. They're exactly like damped oscillation functions. Yes, if you've seen damped oscillations, these are the exact same equations of motion, just like if you've seen spring mass oscillating functions, it was the exact same thing as what we had before with spring mass oscillations, but we don't do that fully. I mean, I might have talked about it in Phys 1, but we didn't really dive into it. Okay, cool. Yes, these are damped oscillations. If you know what questions to ask them now. I know. I asked for questions and I started scrolling down and I saw this bear raising its hand and I thought, how appropriate for this class. We've talked about bears so many times at this point. I feel like we've barely scratched the surface. Do what? It is unbearable, isn't it? And yet here we are. You're still in this class. I know it's because you have to be, but you still keep coming back anyway. Bears for the win, thank you. Any new bear puns? Always. Bear necessities. Upload the Menti slides. Can you upload the Menti slides? Yes, I will upload them. I've been trying to get them out, but I haven't gotten to it yet. If nobody emailed me last time to remind me to do that, please send me an email so I don't forget. Bears for the win, couldn't agree more. Any new bear puns? Not right now. Do you have I have the bare necessities to pass this class. The question is, do you have the bare necessities to pass this class? That's determined by your prerequisites. So was the charge, the total charge in the whole circuit, or just on one of the components? That's a good point, or a good question. But let's go back to our figure here, right? So if we look at this figure, then, that's for the resistor. Let's go back to this one, right? If these are perfect conductors, then that means that the charge is on this plate here, which is what these the solution that we mapped out represented. So this is Q. But that would be true anywhere along this black line here that we would assume, sorry, I don't know where the feedback's coming from, which we would assume has zero resistance. So, so that means for this capacitor, but not necessarily in this inductor, because that would be changing, that would be di dt. So yes, just for the capacitor is the only thing that would be valid for describing. So just for the capacitor. For the current would only be valid for the inductor, right? Because there is no current that flows across a capacitor. You could imagine how much current is flowing onto the capacitor at any given time, but not how much current is flowing across the capacitor. So the safest way to model these in your mind is that the charge equation was for the capacitor, the current being the current through the inductor. That's not a dog. Don't pet that dog. If you go to the Great Smoky Mountains National Park or Rocky Mountain National Park and you try to pet one of those dogs, well, there are TikTok videos posted about what happens when you do that, and it's not pretty. Don't pet that dog. If you're talking about Reese, the canine dog, yeah, I'd love to have Reese back. I need to email Officer Jackie about that. What? I don't know a specific video that you're referencing. I just know that when people... Okay. The inductor causes the current to be a sine wave. Yes. Yeah, you imagine if this was a charged capacitor that was charged in an open circuit that just looped back on itself without any resistance in the wire and no inductor in the circuit, what would happen? Well, it would quickly discharge immediately. So the only reason that there's a sine or cosine wave present is, we said last time, if you remember, inductors act like a momentum term. They act like mass. And so this is where you get some slow drop-off on the charge on the capacitor, which ramps up quickly, but then it overcompensates and it sends too much charge. And so the inductor is what's causing the oscillation here, yes. Otherwise, the capacitor would discharge immediately. What does delta represent? Delta represents a phase offset. If I go back to my Desmos slide, delta here, when I'm moving D, it's going to shift the wave to the right or to the left. But that's delta. So delta is the phase offset. It's going to shift the wave to the right or to the left. Can you post the Panopto from Tuesday? No. There was a technical error due to the microphone not wanting to connect, and so it would not let me record. So I refuse to post the Panopto from Tuesday because it does not exist. Okay. Any other relevant questions? No. Yeah. So what would cause a phase offset in a real circuit was the question, if you didn't hear it. So one thing that could do it is if you had a generator connected to the system at some given time, then you could assume that at time t equals to 0, the capacitor does not have to begin with full charge, right? And so that's going to introduce some sort of offset. Depending on what the initial phase of the generator is, will determine what the initial phase on the capacitor is going to be. That's the simplest way that I can think of to describe it. Okay, let's do some problems then. First, I got to download those problems because I got to talking before class and didn't download problems. So let me do those. I click, but do not drag the button that says download. Anybody know that obscure reference from a mid-2000s movie? It's from Steve Martin's Pink Panther, if you've ever seen that before. There's day 23. Okay, so looking at the problem here, we have what is the period of oscillation of an LC circuit consisting of a 2 millihenry coil and a 20 microfarad capacitor. And we also want to, the circuit that oscillates with an ideal, solely the 80 microfarad capacitor, and what is the inductance needed in order to tune the circuit to oscillate at 60 hertz. And this is problem 29. So let me get to that solution here. One of the things that we discussed last semester when we talked about radial motion is that 2 pi f is equal to omega, and f is equal to 1 over the period t, which is what we're after here. And so you get that t, the period, is equal to 2 pi over omega. And what we just discussed for today is that for an LC circuit, omega is equal to 1 over the square root of LC. Right? So for part A, the period t is equal to 2 pi times the square root of LC. Or that's equal to 2 pi times the square root of 2 times 10 to the minus 3 Henry times C, the capacitor, 20 times 10 to the minus 6 farad. And this comes out to be a periodicity of 1.3 times 10 to the minus 3 seconds, or 1.3 milliseconds for the period. Okay, and then changing things up, basically part B is a completely different problem whatsoever, and it's asking you to solve it in reverse, and you're trying to solve for F equals 60 hertz, or that's 60 per second, another way to think about it. What is the inductance needed if you have a capacitor? Basically, your capacitor has 4 times the capacitance. and solving this problem in reverse where you would have T, which is 1 over F, and you would change this to 8 times 10 to the minus 3. You would have to have an 88 millihenry inductor. Because you're also changing the frequency too. But you can work that out if you want to. Any questions on first problem? Hopefully a little bit more straightforward for all of the complicated mess that we've discussed so far. Okay, number 32. A coil with internal resistance can be modeled as a resistor. So we're talking about the RLC circuit here that we just discussed. Can be modeled as a resistor and an ideal inductor in series. Assume that the coil has an internal resistance of 1 milliohm. So this is way underdamped, is the way you would describe this. It's going to decay very slowly, and the inductance is 400 millihenry. The 2 microfarad capacitor is charged to 24 volts and then is connected across the coil. What is the initial voltage across the coil when you close the switch, that is? How much energy is dissipated in the circuit before the oscillations die out? And what is the frequency of oscillation of the circuit, assuming that since the internal resistance is so low, it's not going to have any, what this is saying is that we can assume that omega here is equal to 1 over square root of LC. So what is the initial voltage across the coil? Well, let's draw this out, right? We've got our resistor, R, is equal to 1 milliohm. Our inductor, where L is equal to 400 millihenry. We're going to assume that a switch is open at first. And we've got a capacitor here, C is equal to 2 microfarads. And the initial voltage across that is equal to 24 volts. And then we come back through here. And what is not stated here is what is the initial voltage across the coil when the switch is closed. We already know that the charge across the capacitor and the current through the inductor are going to oscillate with time, right? That was the solution that we found when we closed the circuit. But if the charge on the capacitor oscillates as a function of time, we know from the definition of capacitance that the voltage across the capacitor is also going to oscillate with time, right? Or that is to say that V is equal to Q naught over C times cosine omega t. And you could imagine then that this is V naught, the 24 volts. So we close this switch here, and we're looking at time t equal to 0. What is the voltage across the inductor? Well, let's do Kirchhoff's rule, right? You get that using Kirchhoff's rule, you would have the voltage across the capacitor is Q naught over C, or that would be V naught, plus R times I plus L di dt equals 0. So what's the voltage across the inductor? Well, to answer that, we have to ask ourselves, when you close the switch, presently, what is the current going through the resistor? What's the current going through the resistor? It's 0, yes, because we said that the current, if Q is equal to A times cosine, not sine, and that was Q naught, sorry. Q naught times sine omega t, then that means I is equal to Q naught omega. I said sine, I know. I'm here. Q naught times omega times sine omega t. If you plug in t equals 0 for the current, that means that at t equals 0, there is 0 current. Right? I mean, for this, t equals 0 means current equals 0 at that time. So what is the voltage across the inductor? You could think of this as V naught is the voltage across the capacitor, plus at t equals 0, there is no voltage across the resistor, plus L di dt, that's going to be the voltage across the inductor, or that means that V naught is equal to minus VL. That means that there is 24 volts, and yes, I know there's a negative sign there, but generally we just think of the magnitude. So we have 24 volts across the inductor at time t equals 0. Just like we'd hope there'd be. Right? I mean, if we go from 24 volts here to 0 volts here, which is what that implies, and if there's 0 voltage drop across this resistor here, that means we go from 0 to 24 volts across the inductor. Y'all with me? Okay. Sometimes when I get the blank stare, the image that comes to mind is Roz from Monsters, Inc. Your stunned silence is very reassuring. It's hard as a professor sometimes, but I do what I can. How much energy is dissipated in the circuit before the oscillations die out? Right? If the oscillations die out, that means that there's 0 energy left in the circuit. Right? So we've gone from total energy to 0 energy. So that means for part B, as complicated as it sounds, how much energy dissipated? So we could say that we'll call this energy dissipated. That's going to be equal to minus the change in energy in, let's say, the capacitor, the electrical energy, which we said is going to be minus 0, because that would be UE final, minus 1/2 Q naught squared over C. Or that's just 1/2 Q naught squared over C. But we're not told what the initial charge is here. We're told what the initial voltage is. And so if you plug in here that Q is equal to CV, or Q naught is equal to QCV naught, then that means 1/2 times CV naught squared over C, or that's 1/2 C V naught squared. So that's, let's see here, 1/2 times 2 times 10 to the minus 6 farad times 24 squared, which is 0. Or let's write it this way, 5.76 times 10 to the minus 4 joules, or that would be 576 microjoules. What is the natural frequency? What is the frequency of oscillation of this circuit? We said that omega is equal to 2 pi f, or that means that f is equal to omega over 2 pi, or that's 1 divided by 2 pi square root of LC. And this comes out to be 178 hertz. So 178 times a second, this system is going to go from positive to negative charge on the top plate. And back again. A hobbit's tale, basically. The first time I ever read The Hobbit was in the 4th grade, and I didn't finish it. I got through, I was like 50 pages in, and we were still celebrating Bilbo's unexpected dinner party, and I thought it was the most boring book in the entire world. If only I'd kept reading. I had no idea that there were dragons and trolls and goblins. I would have had so much fun as a kid. So if you've never watched The Hobbit, you've never read The Hobbit, get past the dinner party and it gets really good. There's like a battle with 5 armies. Turns out it's 1 chapter, but you can squeeze a full 3-hour movie out of it. If you really read between the lines. Okay. This is more pertinent to what we discussed last time. Last time being when we first introduced the idea of RMS currents. And I didn't see this problem when I was selecting problems for our set for last time. So I thought, this is a good problem to work. Because I told you, hey, if you do the integral over the period, then you end up getting the average current. Or if you do the integral over the square of the current and take that average, and then you take the square root of that, you get the RMS. But I just said that, and we kind of moved on. So we thought, okay, let's see here instead and think what could be the average current here, average current and RMS current looking at this problem. So for here, remember you've got the equation for a line if you let y equals mx plus b. Then looking at part A, that means that the current is going to be equal to 4 times time, just in this region right here. And so what we're going to do is we're going to call this delta t. It's going to be a half period, but you can imagine that since this sawtooth wave or triangle wave is symmetric across that dashed line, at least until you complete one period, you get to here, right? That if we can calculate the average over the half period, then we get the same average if we calculate the average over the second half period, and the average of two numbers that are the same. If I have to ask you what the average of 5 and 5 are, then the average is going to be 5, right? So we're going to calculate the average and the RMS over this first half period. And since we'd get the same thing here, since it's symmetric across this dashed line, we're just going to let that be the same. So the average current, this is part A, I average is going to be equal to 1 over delta t times the integral from 0 to delta t of I dt. And we said I is going to be 4t, so that's going to be 1 over delta t times the integral from 0 to delta t of 4t dt. Not exactly like a Cal 2 level integral, but an integral nonetheless. So that's 1 over delta t times 4t squared over 2 evaluated at 0 and delta t, or that's 1 over delta t times 2 delta t squared over, no, we already divided by 2. So just that, or that's, did I forget something? No, that's just 2 times delta t here. What am I missing? What am I missing? What am I missing? That delta t, that second delta t should have canceled out. Because that would be, oh, I think I know what's missing. Yeah, this would have to be in amps per second here. Yeah, okay. Let's imagine delta t is even just 2 seconds or 5 seconds or whatever else you want it to be, right? Then that would mean that there is, let's see, 2 times delta t, so that would be 2 amps per second. I'm gonna have to go back and look at my notes. I was struggling to get all of this prepared ahead of time. I know I've done it, but using the weird units that they've got, it's still worth showing. But the average current 2 amps is what comes out to be the average current, and I've got to figure out where that delta t goes. The RMS current, if you want to see the RMS current, the way that that's calculated is of course. Does anybody see my mistake? I found it. I'm sorry. Does anybody see my mistake? I found where the missing delta t is. It comes from my y equals mx plus b, right? I have to consider that my slope here, which is m, I just said was 4. But it's rise, which is 4 divided by run, rise over run. So my mistake was that my slope m is 4 divided by delta t times time. So that means I would have gotten a delta t squared term right there, delta t squared term right there, which means that this goes away. And there we go. I average is equal to 2 amps. That's how my delta t cancels out. Sorry about that. So what about the RMS? The RMS current. Well, for the RMS current, what you have to do for that is that I RMS is equal to 1 over delta t times the integral going from 0 to delta t of, now we want I squared dt, and bear in mind that we would end up having, we'll have to take the square root of all of this by the end. Right? Yes. What? Well, don't forget that I is equal to 4 over delta t, right? So I'm going to do that same substitution. I've got the square root of 1 over delta t times the integral from 0 to delta t of 4 squared over delta t squared times t squared dt. Or that's equal to the square root of 4 squared is 16 over delta t squared is delta t cubed times t cubed over 3 evaluated at 0 and delta t. And all of this comes out to be, I think, let's see here. It's that's what I get for not. Got square root of 16 over 3. Which comes out to be equal to 2.3 amps. So the RMS does not, in general, equal the average power. I mean, we already saw that with just our cosine wave, where the average was going to be 0, right? But the RMS was non-zero. So the RMS here, which is more akin to the power that you would think about under AC current, you would end up wanting to use the 2.3 amps instead of the 2 amps for your RMS, your average power. One note here: what would happen if you shifted this wave down by the current instead being the same oscillation but going from -2 to +2 amps? The average would be 0, but the RMS would continue to be not 0. That RMS would be like, I'd be on the order of like 1.8 or something like that. Any questions on how we calculated the average and RMS current here? If you want to check at home, the average current for part B is still 2 amps. And the RMS current here is equal to 2.8 amps for this one. Since you spend more time at higher currents, your RMS ends up rising to a higher value. Yes? Yes. That was for our sinusoidal. Yeah, let me think about that for a second. Actually, I don't think it's for sinusoidal. I think it's for when the problem is, what is our peak current here, right? Well, that depends on us oscillating from plus peak to minus peak. This oscillates from 0 to some peak value, right? So because we're not oscillating between plus peak and minus peak, that's where the root 2 breaks down from last time. Good call. That was awesome. All right, enough of my puns and movie references for the day. I release thee. Have a good day.